Thank you very much for the possibility to talk about our recent joint results together with Franz Gmeineder from Konstanz and Patrizio Neff from Essen. Let me first start by considering a deformation phi of a rigid body omega. In a linearized approach, this can be written as identity plus a displacement vector field U. Then the symmetrized gradient of U takes over the role of the infinitesimal strain tensor, so that the corresponding elastic energy is of the following form. To prove then commutativity of the appearing bilinear forms, one needs the so-called Korn-Maxwell-Sobolev, which says that when confound the full LQ norm of the gradient already by the LQ norm of its symmetric part, provided that suitable additional conditions are fulfilled, like the vanishing boundary condition or an integral condition. After establishing coercivity, the well-posedness of suitable minimization problems follows. And one obtains existence, uniqueness, stability, and a priori estimates of the corresponding solutions. Korn developed this strategy more than 100 years ago in linear elasticity in the 2 setting. And this was later generalized to the Q setting for fluid mechanics and the Stokes problem. However, Korn's inequalities failed for the borderline cases Q equals to 1, as follows from the work of Ornstein, and Q equals to infinity, as follows from the work of Mityakin. During the past 100 years, a lot of different proofs and various generalizations to different fields have been given by many authors, including the following: the trace-free Korn inequalities by Reshetniak, the geometric and nonlinear counterparts by Friesike James Müller and its improvement by Conti, Deutzmann and Müller, the case of non-constant coefficients by Neff and Pompe, in the mixed growth setting by Janusz, for example, 2 dimensions, also the wonderful extension by C he showed us yesterday, but also by Lauter and Lukaus in higher dimensions, and also by Conti and Garoni in higher dimensions. Also, Adriana Garoni was here at the trimester program and she talked about these results and their applications. For the case for incompatible tensor fields in Orlich spaces by Lars Dinning and co-authors. For SBD functions with small jump set by Manuel Friedrich or Antonin Chambol, in thin domain by Marta Levica and Stefan Müller, in John domains for Ricardo Duran, etc. and so on. The list is far away from being complete. So a complete classification of the possible part maps which may appear in classical constant inequalities follows from the Calderon-Zygmunt theory. It says this part map appears on the right-hand side of this constant inequality if and only if A induces an elliptic differential operator, meaning that the corresponding simple map is injective. In my talk, I will focus on the case of incompatible tensor fields. But before considering the corresponding inequalities, I want to show you some examples in 2 dimensions, for this algebraic condition of the Calderon-Zygmunt. Okay, first of all, it should be satisfied by the identity, right? Then we estimate the gradient by the gradient, but let's check the algebraic condition. So here the gradient, and for the symbol we replace, instead of the partial derivative, di a multiplication with xi I, like in the Fourier transform, and instead of vectors, consider the action, vector fields, consider the action on vectors A. So we consider this symbol operating on A, which we can also write as rho A times column psi, or we can also write it as a duadic product of A and psi. To prove injectivity, we consider when this expression vanishes. And since psi is non-zero, okay, we conclude that A is 0. Everything's fine. We can estimate the gradient by the gradient. A little bit more difficult is the symmetric part, which induces the symmetrized gradient. Again, consider the symbol, and in 2 dimensions, the symmetric part says that the elements on the anti-diagonal coincide and the elements on the main diagonal remain. So again, since psi is non-zero, we conclude that A has to vanish. The third example, let us consider the deviatoric part, the trace-free part. Again, in 2 dimensions, the elements here on the anti-diagonal remain, and the elements on the main diagonal cancel each other out. Again, since psi is non-zero, we conclude that also A has to vanish. As last example, I want to present the combination of both, the trace-free symmetric part. Actually, in 2 dimensions, the trace-free symmetric part of a 2 times 2 matrix consists only of 2 entries. Yeah? The elements on the anti-diagonal coincide, and the elements on the main diagonal cancel each other out. The trace-free symmetric grading is also interesting from modeling perspective, since it captures the change of the shape of the material by shearing, and appears thus in Coursera elasticity. So again, to check injectivity, let us write this time the left-hand side by a matrix product with entries with psi operating on A. And since the determinant of the appearing matrix is non-zero, we again conclude that A has to be 0. Meaning that the trace-free symmetric part induces an elliptic differential operator. Please remember this for the following slides. Okay, so anyway, life is a little bit more complicated than just elastic deformations, and in gradient plasticity with plastic spin, also plastic deformations appear. So again, in the linearized approach, we take the displacement gradient and decompose it into non-symmetric elastic distortion and the non-symmetric plastic distortion. Then the corresponding energy has the following form, and the control of the dislocations are controlled by the control of curl of P, which enters the plastic energy. Yeah, yesterday we had 3 wonderful talks by Philip, Amit, and Siu about dislocations, and also Roberta will next week talk about dislocations. So, another field of application is the relaxed micromorphic model, yeah, or other extended micromorphic models. Here's a relaxed micromorphic model developed by Neff and co-workers. Here, the micro distortion takes over the role of the plastic distortions, and the last term and the energy is the curvature energy. The relaxed micromorphic model is interesting since it allows for the description of microstructure-related frequency band gaps, but Mohammed will give tomorrow the talk on the relaxed micromorphic model. So, okay, which Korn-inequalities come into play? So first of all, the classical Korn-inequalities strongly rely on gradients not being arbitrary matrix fields. Yeah? Indeed, there is no positive constant C such that you can bound the LQ norm of an arbitrary matrix field by this LQ norm of its symmetric part, even if we assume vanishing boundary conditions. Yeah? Just consider skew-symmetric matrix fields. Meaning that we need a correction term on the right-hand side which captures this incompatibility or curl freeness, and we just can take the curl. The curl, however, could appear with a different integrability P. But in terms of scaling, if we are on the whole space, the optimal constellation of P and Q is that Q is a Sobolev conjugate of P. So, if we test this inequality with gradients, then we will become the classical Korn's inequality. So this reduction to Korn, the presence of the curl and the Sobolev conjugate explains why we are talking about Korn, Maxwell, and Sobolev type of inequalities. And the main issue is the following. Given a space dimension n and an integrability P, an algebraic part map A, and a differential operator B, which is linear homogeneous of Karth order, to classify all constellations of n, p, a, and b such that the desired KMS inequality holds true. So let me show you some of the cases where the KMS inequalities were applied in the particular case when p is greater than 1. First of all, Arnold et al. In 1984 considered in the 2 setting in 2 dimensions the case when a is a deviatoric part and b is a divergence, to develop error estimates in the mixed finite element models. Yeah, similar techniques have been also applied by Carstensen or by Georg Dolzmann. Cha et al. Considered in 3 dimensions, also the case with Dev and Diff, and they used it in the study of the stationary stocks from numerical perspectives. Patrizio Neff and co-authors, including myself, have written several papers on the case when the correction term is the curl, and the part map is mainly the symmetric part or the trace-free symmetric part, but also considered related inequalities like the Dev-Diff case in all dimensions. See the paper by Bauer, Neff, Pauli, and Stark. Franz Gmeineder and Daniel Spector classified in 3 dimensions all possible part maps A when the correction term is the curl. And finally, I want to mention our joint work with Stefan Müller from Bonn and Patrizio Neff, where we state in 3 dimensions due to algebraic reasons. I will touch it on a later slide. And for A being the symmetric part, and we allowed to be the trace-free symmetric part of the kernel. A complete classifications of the possible combination of A and B have been given in a recent joint work together with Franz. Also in all dimensions for all integrabilities b greater than 1, but also allowing for higher order differentials operators like Renner's incompatibility tensor, curl transpose.
Sorry, I can also ask it long.
Okay.
So the result is above, where you have a general P that also applies to P equal 1.
Oh, okay, I will touch it, I will come to it later, okay. So, not always, okay. Okay, so, okay, in my talk, I mainly focus on the KMS inequalities of first type, meaning that I have compactly supported functions or vanishing boundary conditions, yeah. So, we are interested in this type of inequalities, where the function space XAKP is chosen in such a way that the KMS inequality scales suitably. Yeah? So, for example, if B is the first order differential operator, so K equals to 1, then XAKP should be the backspace with the Sobolev quantity. Or if B is a higher order differential operator, then XAKP should be the homogeneous Sobolev space. Okay, let me address 2 borderline cases explicitly. First of all, if B is an elliptic differential operator, then the KMS inequality holds true regardless of how bad the part map A is. Indeed, it could even vanish. So on the other hand, if B vanishes, then the KMS inequality is fulfilled if and only if the part map is injective. Between these 2 borderline cases, a non-trivial abstraction is given by the following example. Consider for a CC infinity function the matrix P phi, which is just the identity times phi. Then its matrix curl is this skew-symmetric matrix. Meaning that the deviatoric part of P phi is 0. Here we have only entries on the diagonal, and they all coincide. And the symmetric part of the curl of P phi is 0. Meaning that there is no KMS inequality with def and zum curl. So this example shows that the differential operator B might turn out non-elliptic on the functions for which the part map vanishes. And in our theorem we stated on the next slide, we show that we basically have to exclude this combination. So here comes the sharp conditions in the case when P is greater than 1. Okay, this is for the first part of my talk. Okay, P equals to 1 is the second part. So let us consider this algebraic part map A, and P being a linear homogeneous half order differential operator. Then the desired KMS inequality with the correct scaling is fulfilled if and only if B is reduced elliptic relative to the part map A, which means that the intersection of the kernel of A with the wave cone of B contains only 0. Also, the last line means that the differential operator B is elliptic for ker A-valued maps. So, okay, with this result, we recover all the previous results I presented you on the previous slide, and generalize them in an optimal way. So let us, as a warm-up, check this algebraic condition for a known combination, mainly for zum and curl. And this was also observed by Dimitri Agiba from Yash. So, in this case, kernel of A consists of skew-symmetric matrices. And the wave cone of B contains only rank 1 matrices. And since there are no non-trivial skew-symmetric rank 1 matrices, the algebraic condition is fulfilled, and we obtain the classical Korn-Maxwell-Sobolev inequality with zum and curl. Okay. So, a few words about the proof. First of all, maybe you have noticed in the theorem, actually just to avoid some visual noise, I say that P has values in Rn times n, and also the part map maps into the same space. Actually, this could be any finite dimensional vector spaces, and they could even be different. Yeah? So, and moreover, on the slides I also present only the proof for k being 1, so b being the first order differential operators. The high order differential operators, this goes then straightforward, we just have to consider high order derivatives. Also, the necessity follows from the necessity of ellipticity in Sobolev type of inequalities, as was shown by Jean van Schacht. So our goal here is this KMS inequality. Yeah? To this end, let us perform an algebraic split with respect to this algebraic part map A into a projection on the kernel of A and a projection onto the orthogonal part of A. Then, since the part map A restricted to the orthogonal part of the complement of the kernel is injective, we obtain the pointwise estimate by the projected part of the orthogonal part of the kernel by the part map acting on it. Actually, we could just trivially add also the missing part to obtain the full part map A of B on the right hand side. On the other hand, B is elliptic on Kerr valued maps from our assumptions, meaning that from classical elliptic regularity we can estimate the LP star norm of the projection onto the kernel of A by the differential operator B, which is in this case elliptic, in the homogeneous W minus 1 P stars theorem. Then perform a triangle inequality, and since LP embeds compactly in W minus 1 P star, we estimate the first term, and in the second term we get rid of this differential operator by lifting this W minus 1 P star onto the LP star. And the combination of these two inequalities gives us the desired KMS inequality. So the KMS inequalities actually were treated most of the time separately, yeah, also developed. And now we have a general approach and only have to check an algebraic condition. So also new examples appear the following way, that we can estimate the LP star norm by def P and the skew curl of P, or it could be def zum P and skew curl plus trace curl, or as higher order differential operator def P and def zum inc, where inc was the incompatibility tensor, or we can also have def and trace inc. So only need to check an algebraic condition and okay. But also new Sobolev type spaces appear. When the part map is in WLQ and BP is in LP. I want to focus on a particular case which we addressed with Stefan Müller on the next slide. Here we stay in 3 dimensions. And, okay, in the precursor paper, Patrizio and I showed that we can write the entries of the derivative of the curl by a linear combination of the entries of the derivative of the trace-free part of the curl. Meaning, the curl of P is in WMQ if and only if def curl P is in WMQ for all integers m. Or that W curl Q coincides with W def curl Q on any open subset regardless of whether it is bounded or not. To our surprise, the situation changes when we consider the symmetric part of the curl. This is what we showed together with Stefan Müller. So if we are on the whole space, then W zum curl Q coincides with W def zum curl Q. But on bounded domains, we have a strict inclusion. So to address the first part, we showed that the corresponding symbols fulfill the displayed estimate. And then we applied the standard Fourier multiplier techniques to obtain the desired equivalence of norms in the whole space. On the other side, this estimate is wrong for complex valued P and Xi. Take this P and this Xi, then their cross product is given by the following matrix, and meaning that the trace-free symmetric part of it is 0, but the symmetric part is not. Then we constructed upon this example suitable suitable sequence to show that the norms are not equivalent. Okay. Let me also say that the KMS-inequalities persist in other function scales. So here the Triple-Lizorkin scales, for example, take this unsuitable condition on the parameters P2, S2, and S1, for A being again this part map, and B a linear homogeneous Kahl-Order differential operator which is reduced elliptic relative to A. Then the KMS-inequality also holds true with homogeneous Triple-Lizorkin spaces, yeah, where the parameter P1 is chosen in the displayed way. Again, to address this inequality, we considered the algebraic split and showed that the appearing Fourier multiplier, where P star is the joint, extends to a bounded differential operator between the desired homogeneous Triple-Lizorkin spaces. So I mentioned this since with Triple-Lizorkin scales we can actually recover the sufficiency part in the Lick-Beck space. Yeah, so for k equals to 1, take S1 and S2 to be 0, and P star, P2 being P, then P1 is a Sobolev conjugate P star. And since a homogeneous Triple-Lizorkin space with the parameters 0, P, and 2 coincides with LP, for all P between 1 and infinity, we get the desired KMS-inequalities in the Lick-Beck space. And now we come to your question. What about the borderline case P equals to 1? Yeah? So, if P equals to 1, then the homogeneous Triple-Lizorkin space with the parameters 0, 1, and 2 coincides with the Hardy space, H1. And we obtain also the corresponding estimate. But note that the Hardy norm appearing on the right-hand side is basically the best that we can obtain with the Fourier multiplier techniques that I presented to you so far, and cannot be proven to be taken as the L1. However, in my title, I promised to catch up with the borderline case. So now we come to the second part of my talk. Now we need a different approach. Okay, here I discuss this borderline case P equals to 1, and for the differential operator B being the curl. Okay, to be honest, for general operators this is still not finished, but okay, the main ideas already appear here with B being the curl. So, okay, our goal now are this L1 KMS-inequality. So this L1 relates to the correction term, yeah, which appears in the L1. So, okay, if we test it with gradients, then we obtain the classical Konstanz inequality, for which we know that A must induce an elliptic differential operator. The question is it also sufficient? Before I answer this question, let me summarize the results that were known in this direction. So first of all, the paper by Garoni, Leoni, Ponziglioni, yeah, we've heard about it so several times, considered the case in 2 dimensions where A was the symmetric part. 10 years later, Conti and Garoni showed that this KMS-inequality also holds true in all dimensions where A is a symmetric part. And finally, almost at the same time, Gmeineder and Spector classified all part maps which may appear in such a 1 KMS-inequalities. Namely, they appear there if and only if A induces an elliptic differential operator. However, we were really surprised that the situation changes in 2 dimensions. And actually, it turned out that the most intricate case is in 2 dimensions due to following counterexample. It shows that ellipticity does not always suffice. So take this trace symmetric part. Yeah, I hope that you remember that this induces an elliptic differential operator. Yeah, perfect. And then for a C-infinity function phi, consider the matrix P phi, which consists of partial derivatives of phi, where they are arranged in such an order that the trace-free symmetric part of P phi is 0, and the kernel of P phi gives minus a Laplacian in one component and 0 in the other. Then the validity of the desired L1 KMS inequality with curl appearing in the L1 norm and the correction term dev zum would imply the contradictory argument where we estimate the L2 norm of the gradient by the L1 norm of the Laplacian, which is seen to be false by regularizations and smooth cutoffs of the fundamental solution of the Laplacian. Meaning that in 2 dimensions we need a stronger type of ellipticity. Yeah? So we were really surprised since we knew this result by Garoni, Leoni, Ponce-Leoni, and it turned out that indeed in 2 dimensions this is the most, this is the hardest case. So here is our main result. This part map A appears in such an L1 KMS-inequality if and only if A induces a C-elliptic differential operator in 2 dimensions and an R-elliptic differential in higher dimensions. So just to recall, R-ellipticity means that the corresponding symbol is injective over Rn for all non-zero real-valued psi, and C-ellipticity means that the corresponding symbol is injective over Cn, where psi is allowed to be complex valued. Also, as short warm-up, again, the classical examples are the symmetric gradient, which is C-elliptic in all dimensions, and the tracery symmetric gradient, which is R-elliptic in all dimensions, but C-elliptic only in dimensions greater or equal than 3. And especially it's not a C-elliptic in 2 dimensions. As higher order differential operators, we have the Hessian, which is C-elliptic in all dimensions, and the Laplacian, which is R-elliptic in all dimensions, but not C-elliptic in any dimension. So, okay. Before addressing the proof, let us relax a little bit and reconsider how we can view this curl in higher dimensions, yeah, from an algebraic point of view, actually just also to avoid indices. So that we recall the situation in 3 dimensions. So in 3 dimensions, the curl is built upon the cross product. Yeah? So, and if we take the cross product with a fixed vector, then this cross product is linear in the second component, meaning that we can find a matrix and write it as a matrix product. And for this matrix, we write NTA, since NTA has the following structure and is especially skew symmetric. Then, from the formal point of view, the curl is just the cross product of the vector differential operator nabla with u, or we can also write anti-nabla times u. Then the matrix curl is seen as a row-wise application of the curl, written again as a curl, meaning that we operate this time from the right-hand side, then the minus sign appears, but we can also write it as matrix multiplication. Yeah? So I prefer to write it as matrix P times matrix with the entries of the nabla. And if P is the 3 times 3 matrix, then curl of P will again be a 3 times 3 matrix, meaning that we can consider its symmetric part, tracery symmetric part, etc. and so on. This is exactly what we have done with Stefan. Of course, we could also consider the operation from the left-hand side, but this will not kill the gradient, but rather the transpose gradient. So, rather to do it, one consider the incompatibility tensor, curl transpose. And from an algebraic point of view, this is just a simultaneous application both from the left and the right. Actually, neither the transposition nor the minus are really needed, and we can, okay, this is not of our interest today. Of our interest today is that we can, with this matrix notation, obtain directly the well-known decomposition of the vector Laplacian into a gradient and a curl, and from this, the usual Helmholtz decomposition follows. And also, Robbins used this decomposition of the vector Laplacian to obtain a direct proof of the different curling. Our next goal is to capture this structure in all dimensions. So, and we will do it inductively. So, first of all, the cross product of 2 vectors from Rn is just a scalar, a1 b2 minus a2 b1. And then we perform an inductive step. So take a vector from Rn and consider its first n-1 components and the last component. And then the cross product of 2 vectors from Rn is given by the cross product of the n-1 components as vectors from Rn-1, and then bn a bar minus an b bar. And despite from the situation in 3 dimensions, the cross product of 2 vectors from Rn returns a vector in Rn times n-1 half. So this is a different space. Okay, anyway, this cross product is also anti-symmetric. And if we with a fixed vector, it's again linear in the second component, so that we can again find a matrix for which we write here the double brackets. Okay, only on this slide, just for formal kind of motivation. So, and despite from the situation in 3 dimensions, this matrix is not a square matrix. Again, so now we are prepared. The curl is again just a vector differential operator nabla with a cross product with U, and the matrix curl is a row-wise application of the curl, and then written as a curl. But note that in the last step we don't have a minus, since the matrix is not skew-symmetric, and the transposition also remains, since this matrix is not a square matrix. We could also consider the incompatibility tensor, etc. So on. This is not of an interest today. Instead, we want to have, again, the decomposition of the vector Laplacian. And with these matrix notations, so without indices, we obtain directly what we want to have into a curl-free part and a divergence-free part, from which also the Helmholtz decomposition in all dimensions follows. And okay, we can also follow Robin's proof of the diff-curl lemma in all dimensions. So now we are prepared for the proof, first of all, in the higher dimensional case when n is greater or equal than 3. In the first part of my talk, we considered an algebraic split with respect to the part map A. And now we consider an analytic split with respect to the differential operator B. Here's the curl, and take the Helmholtz decomposition into a curl-free part and the divergence-free part. But then, the curl-free part is just a gradient. And for gradients, we have the classical Calderon-Zygmunt. And the gradient was chosen in such a way that it's a curl-free part, and then just by triangle inequality we obtain the last step. Meaning that it only remains to show that we can bound the L1 star norm of the divergence-free part by the L1 norm of the curl. But this is a non-result. This is a Bourgain-Brizy type estimate, yeah? Which says exactly what we want to have. That you can estimate the divergence-free part, that you can estimate the L1 star norm of a divergence-free vector field by the L1 norm of the curl of F. And since the matrix differential operators act row-wise, we obtain the desired estimate in dimensions greater or equal than 3. However, Bourgain-Brizy is wrong in 2 dimensions. So we need a new approach. Yeah? And we achieved it by the classification of C-elliptic differential operators in 2 dimensions in the following way. Namely that there exists a linear part map L and a scalar valued linear function gamma and an invertible matrix G such that the almost complementary part projects onto a line in GL2 into the direction of G. To address this characterization, we considered the action on the duadic products of the basis vectors and constructed this linear part map L and the entries of gamma explicitly using the interplane between C-ellipticity and cancellation. Okay, now we are prepared also to finish the proof in 2 dimensions. Take this decomposition and apply the 2-dimensional curl on both sides. Yeah, note that G is a fixed vector and gamma is a scalar function, so we can even interchange their order, so that the curl gives us the following expression. And multiply with G from with the inverse of G from the left-hand side, and let us curl the left-hand side the blue fracture F. Then, taking the divergence on both sides will kill the term with gamma, and we obtain that we can express the divergence of F by a second-order differential operator B, y tilde B, acting on the part map A of B. And now take the strong Bourgain-Brizy, here displayed in 2 dimensions, which says that one can estimate the homogeneous Wy minus 1, 2 star semi-normal F by the divergence of F in the homogeneous W minus 2, 2 semi-norm plus F in the L1 norm, and apply it to our blue fracture F. And since the blue fracture F was something like the curl, we obtain the last step, where in the middle term we got rid of the second-order differential operator y tilde b by lifting this W minus 2, 2 norm to the L2 norm. And the right-hand side is already as desired. So, okay, to conclude, consider the Poisson equation with the right-hand side being the curl of P. Then it follows from elliptic regularity theory that one can bound the L2 norm of the gradient of the solution by the homogeneous W minus 1 2 norm of the Laplacian. But the Laplacian was chosen in such a way that it is the curl of P. And for the curl of P in the W minus 1 2 norm, we had the estimate from the previous slide. Finally, take the auxiliary function T, which consists of partial derivatives of U, where they are arranged in such a way that the curl of T is exactly minus the Laplacian, meaning that T minus P is curl-free and can be written as a gradient. Okay, now take P and perform trivial addition of 0. T minus P was the gradient dV. For gradients, we had the Calderon-Zygmunt. You can estimate by the part map, which induces an elliptic operator. dV was T minus P, so we get an additional term of the Lebesgue norm of T. And T was chosen in such a way that its entries actually coincide with the entries of the gradient. And for the two norm of the gradient, we had the estimate on the lines above. And here it is. Here is also the 1 KMS inequality in 2 dimensions. Okay. In my talk, I mainly focused on KMS inequalities of first or first type, not first order, or first type. So let me comment in the remaining 5 minutes how this classification of C-elliptic differential operators allows also to obtain the KMS inequality of second type, meaning here in this case that there exists a finite dimensional subspace K of the R2 times 2 valued polynomials such that for any open bounded simply connected Lipschitz domain we have this KMS inequality of second type, meaning what is the difference to a KMS inequality of first type is that P is no longer compactly supported. And here the correction is that we subtract the elements from the null space of the right hand side on the left hand side. And this KMS inequality holds true if and only if again A uses a C-elliptic differential operator. To address this KMS inequality of second type, we need another auxiliary result, namely a Lyon lemma or nature's estimate. So which one of the Lyon lemma I mean? So in this case, I mean if f is a Lebesgue in LQ, then by the definition of the dual space, f and the derivative of f both lie in W minus 1Q. The Lebesgue, the Lyon lemma I want to use suggests that on bounded Lipschitz domains, also the converse holds true, and which can be expressed also by the nature's estimate. By the way, this nature's estimate is one of the fundamental tools to prove Korn-type inequalities, also in other contexts. So take our decomposition and apply the L2 norm on both sides. And then we use natures to estimate the L2 norm of gamma by the W minus 1 2 norm of gamma plus the W minus 1 2 norm of the gradient of gamma. And since the partial derivatives of gamma are linear combination actually of the curl of P and curl of L of A of P, just take the curl of the first line, or maybe you remember it from the previous slide, we obtain an additional term of the L2 norm of A of P and the curl of P in the W minus 1 2 norm. And gamma actually was something like the almost complementary part. And I want to focus your attention on this W minus 1 2 norm of this almost complementary part which appears in the middle. Indeed, it is crucial to derive from this line the Korn's inequality. So besides of this middle term, the right-hand side is already designed. Yeah, we just have to estimate the curl of the W minus 1 2 norm by the part map A of P, the 2 norm plus the curl P in the 1 norm, but we know how to do it. So to eliminate this middle term, we can either assume vanishing boundary conditions. This will give us Korn's inequalities of first type, or subtract the elements from the null space of the right-hand side on the left-hand side. And this is what we are going to do now. So we consider the null space of the right-hand side, meaning that we look at matrix fields which part map vanishes and also whose curls vanishes, meaning that these are actually gradients with vanishing part map. But A was a C-elliptic differential operator, and it follows from the work of Smith that then the null space is indeed finite dimensional, and this is what we need to have. Then there exists a basis E1 to EM of the null space and the dual basis L1 to LM of linear functions on K, which we extend by Han-Banach to linear forms NL2. And I claim that we can bound the L2 norm of P by the right-hand side as desired, plus the absolute values of the linear forms of P. Okay. And we prove this by by contradiction. Yeah. So this idea to prove such an inequality is actually also very old and goes back to Kondratiev and Lenik, who used it also in the context of Korn-Maxwell-Sobolev. So let us assume that there exists a bounded sequence of matrix fields Pk such that the right-hand side turns to 0. Then after a subsequence, Pk converges weakly in L2 to P star. And we also have that the part map A of P star is 0, and the curl of P star is 0 in the distributional sense, meaning that P star is indeed from the finite dimensional null space K. And since also the linear forms of P star are 0, we conclude that P star has to be indeed. This means that the almost complementary part converges weakly in L2 to 0. And since L2 embeds compactly in W minus 1, 2, we have that the almost complementary part converges strongly in W minus 1, 2 to 0. And this gives us the desired contradiction to an estimate we had on the previous slide. Namely, the left-hand side remains bounded from below by 1, and the right-hand side tends to 0. Then, okay, we just subtract the projection of the null space on the left-hand side, and we obtain the desired KMS-inequality of second type. So in the last 40 minutes, I talked so much about Korn-Maxwell and Sobolev. So here are the picture of these three men. Thank you. Not only goes to them, but also to you, to the audience, for your attention. Thank you very much.